All right, here we go, calculating triple integrals. So just like in 2D, Fubini is here to save us. This definition of the triple integral is a bit crazy. We don't want to do that, be taking a bunch of limits and chopping things up into little boxes. So thank you, Guido. He's going to bail us out. Basically, the way this works is I have some kind of like sort of a little building here, and we're going to do the laser beam method. So I'm going to imagine that the building kind of has a simple floor plan here in the XY plane. And then since we chose to do DZ first, you're going to draw a laser beam up in the direction of the Z axis right here, and it's going to enter the region at Z equals 0, and then go up here and exit the region at the function. And so our limits of integration here are going to go from 0 up to the function. Then once you're done with that, then you just completely forget about the 3D picture, and you can just focus on the 2D picture. So now we're going to do dy next. So what I'm going to do is draw a line that's parallel to the y-axis here. And you can see where it enters and exits the region. So that's where we get these limits of integration. And then the last thing, I guess there is technically just kind of a one-dimensional picture here on the x-axis, and we think about what part of the x-axis we use, and that's just this part right here, everything that bounds the region. And so our limits are going to go from x equals a to x equals b. I've just drawn an example here. I think you can see that there are many different ways that you can choose this order. It doesn't always have to be dz, dy, dx. This is the default. There'll be times where you're going to make other choices, and I'm going to go over some examples about why I would make a different choice sometimes besides doing this order right here. Let's work through this example where we find the volume of a tetrahedron. It's very common for these problems to be restricted to the first octant. It just makes them a little bit easier to work with. So I've got here this plane graphed, and you can see the way that I graphed it was I considered all the level surfaces, and I've also got the computer graphing it here. So you can see it goes out the farthest on the x-axis, and then a little bit less on the y-axis, and then a little bit less on the z-axis. That's because when you calculate these intercepts, like if I put a z and x equal to 0, then I would just be left with 2y equals 6. So then you divide by 2, you get y equals 3. So that actually the bigger the coefficients are here, the smaller these intercepts are going to be. You can see the z coefficient is the biggest and the z-intercept is the smallest. So after you got the surface graphed, then we decided to do dz, dy, dx because it's the default and it works this time. So I shot a little laser beam up through the floor of the region, and it intersected the solid at z equals 0 and left at this equation right here. You can see I just solved the equation of the plane, this equation of the plane right here. I just solved this equation of the plane for z, and that gave me a explicit function for the surface here. Z equals. And then after you're done with the 3D picture, then you just move on to the 2D picture. And so then you can see I just shot a line parallel to the y-axis, and then I just solved that equation for y. It enters at 0. It exits at the equation of this line right here. And then now you draw a 1D picture. This is kind of nice. You can see we start with a 3D picture. We do the first integral. We get a 2D picture. We do the next integral. Then we get a 1D picture. So it's kind of a nice pattern. Just makes me feel good. Every time I find limits of integration, I decrease the dimension of the drawing that I'm making by 1. decided that I didn't like the order that this was in. So one of the nice things about Fubini's theorem is that it actually also tells us that the order that you choose will always give you the same answer, so long as you can still set up the integral. So here I've set it up again. This work is a bit sloppy, but I think you guys can follow it. This time I chose to do dx first. So you can see here, this time I shot the laser beam down the x-axis this way. So it enters and exits at x values, and then after that, then I drew a 2D picture. You can see, since I chose dx first, this 2D picture has y and z in it. So whichever variable you choose to integrate with respect to first, then the next drawing will be missing that variable. And this pattern continues. You can see the last integral here. Then next I chose to do dy, so the last limits of integration will have z in it. All right, let's go ahead and work this out and see what we get. All right, let me just walk you through my calculation here that I totally did not make an arithmetic error on, and 100% did not accidentally add my fractions wrong. So what happens is you basically just go about calculating the integrals just one at a time. So first I needed an antiderivative of 1 with respect to x, so that gave me x. And then I just plugged in 0 in those limits. That's easy because you're just left with those limits there. Now it gets a little bit more complicated. Now I'm doing an antiderivative with respect to y. So you can see here 6 became 6y. Antiderivative for 2y with respect to y is y squared. And then 3z, remember 3 and z are both just constants here. So it's just going to be 3z, basically just put a y there. Then you plug in these limits of integration. This got a little bit ugly for me here. What I decided to do was reduce this so that it made it easier for me to FOIL here. That's how I figured this out, is I FOILed this. Combining a bunch of like terms, and then you just plug in the limits of integration. You end up with 6.